This project ends with the construction of a permanent version of our circuit using a printed circuit board and a protective case. Breadboards are great for building and testing, but they are fragile. Wires can disconnect and signals can become unreliable. A printed circuit board solves this by allowing us to solder components into fixed positions, creating permanent, secure electrical connections. The board includes pads for all components, the chips, resistors, capacitors, and power connectors. These include a 0.1 microfarad ceramic capacitor to filter high-frequency noise, a 100 farad electronic capacitor to smooth voltage changes, two 1,000 ohm resistor networks to protect the display segments, and two position terminal block to connect power. After soldering and confirming the circuit works, we mount the board into a custom plastic case created by the previous ACE students and printed in the design studio. A 9-volt battery fits inside the compartment powering the entire case. Electrical tape is added between the battery and the board to prevent short circuits. The case is then closed and screwed shut, creating a strong and portable version of the device. This step brings together electronics design and real-world reliability. The user interface begins with a momentary push button, normally open. When the button is pressed, it closes briefly, sending a signal that advances the count. The circuit uses a pull-up resistor to keep the input pin at a high voltage when the button is not pressed. Pressing the button drops the voltage low, creating a clear pulse. This method prevents the pin from floating, which could cause random behavior. The button gives user full control over when the count changes. Clock signal for the circuit is generated using a NAND gate oscillator, built with the 4011 integrated circuit. The chip contains 4 independent NAND gates. By wiring 2 of them with resistors and capacitors, we create an oscillator. This oscillator changes and discharges a capacitor through a resistor, which produces an analog voltage. The NAND gate switches the output from high to low dependent on the voltage, creating a repeating digital square wave signal. The signal becomes the clock pulse for our counter chips. The resistor and capacitor values control how fast the signal oscillates, changing them just how quickly the circuit counts. The 4017 is a decade counter. It has 10 output pins and counts from 0 to 9 in sequence. Every clock pulse from the NAND gate moves the high signal to the next output pin. In this circuit, we use it to alternate between counting up and counting down by linking its outputs to the direction control of the next chip. The reset and enable pins must be conditioned. Reset must stay low unless we want to restart the count, and enable must be low to allow counting. In the binary up or down counter, the 4510 chip receives pulses and produces a 4-bit binary output. This binary number increases or decreases depending on the direction pin, which is controlled by the 4017 chip. It can count from 0 to 9 and wrap around 0 to 15 and wrap around either direction. It's basically shown in this one by the 4 LEDs and in binary code, as you can see here. The 451 chip converts the 4-bit binary output into signals for a 7-segment display. It has 3 control pins that must be set for normal operation. Blinking must be high to allow display, the latch must be low to update in real time, and the lamp test must be high to avoid turning all segments on at once. This chip handles the logic of translating binary numbers into segment control signals. The display shows decimal numbers from 0 to 9. It has 7 individual LEDs arranged in number 8 shape. The type we use commonly cathode display, meaning all negative sides of the LED are connected and grounded. The decoder chip turns on the correct combinations of segments to represent the number. Each segment needs its own resistor to limit the current and prevent damage. Without resistors, the LEDs can burn out or appear uneven in brightness.